Да.
Okay, let's start. Today we have talked due to Alexander Zaitsev about topological triviality of automorphism group.
Okay, thank you very much for the opportunity to give a talk here. Yeah, I will be talking about topological simplicity of such a group. This talk I'm giving is following to Jeremy Blanc, or Blanc, better to say. And I want to start from the very definition. So let K be a field. Let me briefly remind that out K.
Any field.
Yes, any field in any precise lemma I will say is it infinite or characteristic zero if needed. Okay, but so far it is any field. Okay, and just a group of automorphisms is a group of such map to F1 xn, F2 xn, and Fn of x1 xn such that okay, Fi's are polynomials xn, and there is an inverse. Okay, so
Polynomial inverse, right?
yeah, polynomial inverse. The F1 inverse is also a polynomial of this form. Well, and later I will be writing this fx equals F1 Fn for shortness. Okay, so here we have a subgroup, normal subgroup, which is denoted by alt k n. This is just maps or automorphisms which has Jacobian equals to 1. Okay, another description of this subgroup is the kernel of Jacobian map. Yeah?
It's more familiar to us is that this SAut is a subgroup generated by all GA subgroups.
Okay.
Is it the same?
No, it is an open question.
Question whether it's the
Yeah,
same.
If you have some group generated by GA, then
Of course,
all
Jacobian is-
Jacobian are used. But
The opposite is open.
opposite is
Okay, thank you.
Yeah, I think that there are a lot of people who know about this more than me, so I'm best to be happy. Okay, so this is the definition, and the theorem I want to talk about is the following. Theorem A, which is the main, or one of main theorems from Blanc's paper of previous year. It states the following. Let K be an infinite field. Let K be an infinite field. And n some positive integer number. And if we take, I say something, something will be unclear here, but I will comment later. If we take non-trivial normal subgroup, which is moreover closed, is a closed normal subgroup. Then n contains all tame automorphisms. With This means that SAut of A2 is simple as an ind-group. As an ind-group.
Because all the automorphisms is tame.
Yeah, exactly. This in particular follows from the fact that each automorphism is tame. So what should be unclear for a moment is this word closed. Maybe for someone forget what is tame. And simple as an in-group just means that with topology of this group, there are no normal closed subgroups. So this again corresponds us to this place. Okay, but actually,
I'm sorry for comments. This is a very interesting because tame depends on generators, but for any generators, all the tame automorphism is on.
I will define tame in a moment. So maybe I know not general definition, but some precise definition.
Okay.
So again, this word closed is important, of course, in all this story, but actually I don't want to speak much about topology, and I will explain about topology of this group at this point where I need it. It will be much later, and tame I will explain in a moment after some historical remarks related to this question. Maybe it is important to know that what happens without topology? And without topology, this group is known to be non-simple. I mean, there are some abstract normal algebraic normal subgroups there. Abstract subgroups, yeah. And this is the result by due to Danilov. Let me write like this: SAut K of A2 is non-simple as an abstract. Okay, and moreover, this. Okay, let me write Danilov. 1974. Yeah. And then it was this result was generalized.
So this is about this is only about n equal to 2.
Yeah. Only in for n equal to 2. If question comes, then let's say that this question right like this, more or equal to 3, simple or not, this is open question. Okay.
Even in the setting of an abstract group.
Yeah. This is all about. This is without topology. Yeah. Okay. Example of Danilov was generalized by some other guys, but let me give another remarks. What happened with topology? There was a paper by Shofalevich in 1981, which claimed that SAut K of n more or equal to 2 is topologically simple. But if one can say that this is contradiction, yeah, because I mean not contradiction for a moment, but why are we interested in this theorem because of this result? But it turned out that there was a mistake. Here.
Sorry, topologically simple is
yes.
Simple as a topological
Yeah.
is.
Yeah.
This is the same.
Yeah. I mean, we consider the topology here and consider normal closed subgroup there. And there are non-trivial. Yeah. This was exactly this result,
Okay.
but even in higher dimension too. But it was wrong, unfortunately. But anyway, there was a lot of nice work, so let me write it here. Okay. So this is some remarks related to this theorem.
And this is still open.
Yeah. For higher dimensions, it's still open even after this work. But actually, if you can see, the first step is given here because about all tame automorphisms, I'm saying in any dimension.
Yes, but this is not.
Yeah, of course.
Gives, the answer.
Yeah, of course. It relates us to other open questions. Not open, but a lot of work should to be done. Okay. So for a moment, I want to present two other theorems which will imply theorem A. Okay, theorem B, which is also due to Blanc in the same paper, which states the following. Again, let K be an infinite field. And integer number for nouns greater than 2. Greater or equal. And let, again, n be a normal, again, closed normal subgroup. Be a closed normal subgroup. Then n contains all translations. Okay, where translations is just a translation by a vector. Okay, and actually, this is kind of main result, and this is a corollary due to the following theorem, which was stated at 220. Theorem C, which is due to Drew and Lewis. And this theorem doesn't require any topology. It's just an abstract group abstract theorem. Let K be an infinite field again. Okay, I'm restricting here for infinite fields, but some results work in more general situation, but I don't want to overload here. Okay, field n again is integer which is greater than 2, greater or equal, and n is just a normal subgroup. Okay, n just normal without the function. So then first thing we can say that if n contains all translations, then n contains SLN. This is the first thing, and the second is if n contains SLN, then n contains all tame automorphisms.
Theorem C is rather clear because all the generators of tame automorphism with Jacobian equals to 1 is GA subgroups, and they are conjugated to translations. This is the idea, am I right?
Yeah, but with actually, I wouldn't, or maybe would comment a few words about theorem C, and the main goal for us will be theorem B. But let us note for a moment that B plus C implies A immediately. Just let's have a look. We have the same setting. Okay, n equals 1 is easy case, so let's forget about it. In other situations, what do we have? We have a closed normal subgroup, yeah. If it's closed normal subgroup, then it contains all translations, then it contains SLN, then it contains all tame. Okay? Is it clear for now that we need to prove only theorem B and C? Okay.
So the implication is just trivial.
Yeah, implication is just trivial. So, okay. Unfortunately, I want to have theorem B for a longer time on the board. Okay, so should I remind for someone what is tame automorphism? Okay, we decided that I know another definition. Okay, for me, tame
I think
automorphisms.
that definition is
Okay, for
is
me,
the same.
tame automorphisms are just automorphisms which generated by affine and triangle.
Yes, what I tried to say that
Yeah.
the concept of tame automorphism, of course, depends on generators. So you have a coordinate system,
Yeah.
and then affine and triangular.
Okay.
And this theorem is rather interesting because tame automorphism are different. They are not normal subgroup. And if you consider another system of generators, you have another tame automorphism, and all of them is contained in N. And this is just was my comment. Nothing about.
Okay,
So
definition of
probably it
tame.
would be better if you recall.
Okay, yeah. Let me recall briefly. So, okay, let me recall the following. Some. Okay, it is briefly so. Classical subgroups. In automorphic group. Even let me write here even R, where R is an integral domain. It is clear that the same definition works not only for field but for integral domain too. Okay, so we have GLN of R. We have translations, which I mentioned already. But let me write it down. V1, xn plus vn, where vi is an element of R. Okay, so affine, which are generated by this two translations. And the last one, previous one, last one, triangle automorphisms are the following. We can write them like this: A1x1 plus B1, A2x2 plus B2, ANxn plus Bn, where AI's are invertible elements in R, and BI's are polynomial, but depending on different number of variables, and more precisely, are these polynomials. Okay, so B0 doesn't depend on any variable, B2 depends only on the first variable, and so on, so on, so on. Okay, and finally, you can have a look last time on this theorem, and I will write this, but actually we will prove theorem B, so not much.
So in this definition, it depends on the choice of the system of generators, right?
Of course.
Yes, of course, but let me do it in coordinate way. Let's fix some system of generators x, y, xn, okay? And
It depends up to conjugation, yes, so.
Of course, yes.
yeah.
It's
Okay, I
not a
understand.
normal subgroup.
I understand what you mean, but okay. So, and the last thing I want to say in historical part.
So is it true that it is not unique? So, so if you take another system of
If you
generators,
take another system, you have another tame, and
Another-
by this theorem, it's also in this subgroup.
It is no surprise because n is normal. It
Yes,
contains
yes.
all conjugated subjects.
Yeah. Okay, so let me remind some results of this, and then we go to proof of theory. So, what is known? Of course, this is boring for experts, but I wish for someone it will be useful. Jung and other Kulk in years 1942 and 1953 respectively. This is, if I'm not mistaken, over fields of coercivity 0, and this is over arbitrary fields. The result is the following: that all group of automorphisms coincide with its tame subgroup. Tame subgroup coincide with all group A2 over any field. Okay. Because this is important, there is theorem by Data, which doesn't relate to Data automorphism. But a paper is the same, where Data automorphism appeared. It states that tame over ring of polynomials is not the same as the all automorphism group over this ring. This is strict subgroup. Okay, actually I don't know what I need to require from the field, so sorry for this. No, I don't. And the last thing is which is also related to Data, but due to Shestakov and Umerbaev. And they proved that in dimension 3, this theorem fails. That K of A3 is a strict subgroup in out K A3, where K is field of characteristics. Okay, so that's it.
so did they also construct non-tame automorphism?
Yeah, they proved that negative automorphism is non-tame. In what? No, negative automorphism. This theorem,
This
this
is not
negative
negative
theorem.
I see.
Yeah. This related to this.
So in the same paper, they
Yeah, it's just in the
constructed
same
a-
paper he constructed it.
This is an explicit automorphism.
Okay, so this is all about the historical part, and
And for greater than 3,
it's
subgroup.
open to thank you. If we replace here 3 for great ring integer, this is unknown. Is it strict or not strict subgroup? Okay. So, well, actually, I want to erase this this all, and let me just
I didn't
fix.
catch you. Will you prove theorem C?
I wouldn't prove. If I will have time, I will comment on it.
Okay.
But I will prove theorem B, and let's hope to this, we are going to find in any normal subgroup, non-trivial, closed normal, like, first of all, we will try to find any translation, then try to prove that all translations are there. This will be our goal. So now I want to present our main tools or our main strategy to do this. Okay, sorry for erasing this. I wish everything is clear. Okay, and our main tool will be family, something what's called families of automorphisms. Families of automorphisms. Okay, what do I mean by these words? I mean the following. Imagine that we have some element of this group, out k of t of an, and maybe phi from here and psi from here, out k of t and t inverse, Taylor-Run polynomials of an. But then clearly this gives us a morphism from A1 to automorphisms over the base field, yeah? Which works just, you have coordinate t here and maps it to phi of t, yeah? And the same thing we have here, by the same rule. But, sorry, from the posture line. So this morphism which we can correspond to these elements. Okay, then imagine that you have some be a normal closed subgroup. Also, let me note the following. First of all, I have no letter S here yet. I'm working for a moment with all automorphism group, but it doesn't matter. And one thing I want to note also is that if you're not used to take automorphism, you can forget about it because we will be finding only translations. So actually, the rest thing will be really simple. But okay, if we have such a normal closed subgroup, we have nothing. Okay, let me require that this is again non-trivial. So the only thing that I have, I know that there is some non-trivial element and nothing more. Okay, so I can take some non-trivial element. Okay, and I need to do with this something to obtain new elements in my group. Okay, but it's clear that okay, my group is normal, so I can try to conjugate by some elements. But also it's clear, okay, it's not a mathematical statement, but if I will do something, if I will conjugate by some finite number of elements, I wouldn't get something new because I wouldn't use topology here. So I want to try to conjugate this F by some family of automorphisms. And by family I mean precisely this. Okay, this image of this and image of this. Okay, so let me write this down. Can produce new elements of like this. If we conjugate, okay, f also lie in here and in here too. Yeah, you're right. Just doesn't depend on t, but this is not bad. And we can construct a new element here and here just using conjugation. K of t an and psi inverse f psi in here. T and 1 over t. And again, by the same rule, we get map from here to here and map from here to here. Okay. But sometimes it turns out that this map extends to all affine line. And you can imagine like this. Sometimes element of this group becomes also lie in the smaller group, which is just polynomial ring. Yeah, you can conjugate your some element by other elements, and it turned out that this thing doesn't depend on inverse of t in all its contents.
So it contains no negative.
Yeah, it contains no negative powers. So sometimes it happens, sometimes no. But if it happens, then you can extend your this morphism to this morphism. Okay. And let me give some examples of families, and then let me give an example of this picture when conjugation by something which had negative powers of t.
So is this a sort of taking limit?
Yeah, of course it's sort of taking limit, but if you give a precise,
Is it where we use the topology? Or not?
yeah. This is exactly this trick where conjugation by a punctured line extends to the full line. This is the main thing where we use topology, and we will see it later. But we'll show it in a moment. Okay. So, yeah, examples. Even of one parameter families, so say first example is from polynomial ring. Tau is just x1 plus tv1, x2 plus tv2, and so on, xn plus tvn. Clearly lies in automorphism over polynomial ring of an. Okay, and the second one is
K of t or K of x?
K of t, of course. Thank you. Of t, yeah, everywhere here is t. Okay, and alpha is from Dokladчик line. T x1, t x2, t xn. T and t inverse. Okay. So here example, this is the family of translation, and this is family of homophysis. Okay? And now I want to take some element from automorphism group over a field, and conjugate by the family of homophysis. And I'm trying to figure out this picture. Let me show it. Okay, lemma, which is not related to theorem B, but I think that this is the most clear and the most related concept which we will use there. Okay, let K be just a field, N be again a positive integer, and automorphism over a field of affine space. Okay, and let me require also that f preserves 0. Okay, so also define the following conjugation. G is element which is obtained by conjugation by alpha, this alpha of my f. And T of A. Okay, so far this element like here. But the statement is that then in the setting G actually lies in automorphisms over polynomial ring, not over Lorentz polynomial ring. And moreover, and G of 0 is a linear part of F. Part of F. Okay, so actually, if someone think a couple of minutes about this, this is not really strange, but also this is not strange too. But this, let me just say that this is an example of kind of this picture. Yeah, you conjugate by something. Here we had by alpha we had a punctured family. Yeah, we just had a map from A1 without 0 to all automorphisms. Okay, and then we conjugate some element by this family, and it turns out that actually this element gives you a family extended to the whole line.
I'm sorry.
Yeah.
What is the define? Means that
Oh, okay.
suppose that we
Put.
define we can put. So for this is for
For some arbitrary thing,
uh-huh.
I put G by conjugation by this automorphism.
Okay.
Family.
And we
Yeah.
consider this automorphism.
Yeah, we consider just this automorphism. Initially it lies here, yeah, by
Yes.
definition, because we conjugate by the elements from here.
But you assert that it lies in
Yeah.
K of T.
Yeah, yeah. It means that this, if you write down the coordinates, coordinates wouldn't depend on that will
This is
be,
true for any automorphism over K.
but only preserving 0.
Preserve the
This is important.
So, let me ask you.
Yeah, yeah.
Is it obvious a priori that the linear part of F is also not an automorphism of A?
Yeah, yeah. Because if this happens, yeah,
Yes.
then you have differential
Ah,
0,
yeah.
and it also would be inverted.
So the
So
point is that it can be obtained by such a family of.
yeah, yeah. The geometrical picture will be the following: you take some f inside automorphism, then you can draw a
The
line.
point is that the linear part also belongs to the same normal subgroup.
Yeah, yeah.
Right?
This is a more strong thing which neither I want to say. First of all, I want to say that if you have some f here, you can draw an affine line which connected to its linear part. Okay, linear part. I think that this is also pretty.
Ah, yes.
Yeah.
That's right.
Yeah, I think that that's very standard thing, but let me prove it too. Okay, so if we have our f, we can write it like this: f1, fn, and each fi we can split to homogeneous part. Yeah, I mean decompose to homogeneous part. Let me write like this: fi is equal to fi1 plus fi2 plus fid, where index d is the greatest of all degrees here.
There is no fi0 because
Yeah, there is no
0
fi.
is
Yeah, exactly. There is no fi0 because of this condition. Yeah, and let me.
So with the homogeneous part.
Yeah, this homogeneous part, and I'll even write
And the
here.
linear part is fi1.
Yeah, linear part is this. Okay. So where fij belongs to homogeneous part polynomial ring. J homogeneous part. Okay. So we always can write like this. Okay, then let's write down how G looks like. Okay, if we present G like this again, G1, Gn, we can see that Gi is equal to fi1 plus tfi2 plus t in power d minus 1 fid. Just this. Let's figure it out. We just multiply all coordinates by t, take an f. Each homogeneous part get t in front of this t in power of this of homogeneous degree, and then we divide by t. Yeah. So each degree drops by 1, and in front of linear term we have no t. Clear? This is almost this condition. Let me note the following thing. If we have no t's in my presentation, this is not enough to claim that G lives here. Why? Because I need that inverse of this element living here too. But from this conjugation, we see that the inverse looks like conjugation of f minus 1, and it also doesn't have t in denominators. Yeah. So actually, we prove this, and g of 0 equals to the linear part also clear because of this formula. Yeah. So this is an algebra, but geometrically, again, it is really nice picture that we can connect your initial automorphism with this linear part. In this lemma, there was no normal subgroup, no normal closed subgroup, but as already mentioned, if there was a normal subgroup in the story, yeah, then everywhere except 0, okay, so this is g of 0, and everything everywhere else is g of something else. But these elements, they were obtained by conjugation, but some real automorphism, which correspond to g of t, to this
to some particular value.
Yeah, to some particular value of t. And this is not. But if you imagine, this element also will lie in this normal subgroup by continuity arguments. Okay. I will explain it later again, but this is the main tool. Why everything works. And we will control this element at 0. And in the punchline it will be the translation exactly. So this is our method. Again, this is how it looks like, and now I think I'm ready to prove theorem B, but starting from some technical lemma. And the technical lemma is related to this question. Is it true that the inverse of some of my automorphism really also doesn't depend on t? So, how much time do I have?
40 minutes.
Okay, I will try. 15, 14 minutes.
Even 42.
Okay, so technical lemma. Maybe let me call it lemma 2, not to think about this lemma. Okay, and let me have a look. I'm sorry. Just to say, just to be more, maybe more clear again. Maybe I want to spend 5 minutes on a sketch of proof of theorem B. Sketch of proof of theorem B. So, if you remember, there was some normal closed subgroup, and I want to show that all translations are there. And the only one thing I can do, I take some element which is not identity. Okay, so there are 2 cases. If F is already a translation, then I claim that all translations lie in M, because since just SLN of K acts transitively on translations without identity by conjugation. This action is transitive. And if I have some translation, then by conjugation of these elements, I can obtain all translations. Okay. This transitivity is exercised, so the interest part of course, if F is not a translation. F is not a translation. Then I want to write only a picture. And the picture looks like following. Imagine this surface is a subgroup N, and the ambient space is SAut. Okay, and in the ambient space we have some families like parameterized by A1 and some punctured A1, like previously. A1 without 0. Sometimes there are one parametric subgroups, but not always. What can we do with this element F? Yeah, of course we can conjugate by this thing and by this thing, get some images of affine lines. Also we can shift it by some multiplying by F or power of F, something like this. And also each of these elements we can conjugate by this thing. And think with which I want to show that sometimes we can conjugate some special elements, let's say element G, by punctured affine line in the following way. So we would know that away from 0, this is a conjugation of this element by some elements. And at 0, we would know that this is a translation. But by continuity argument that this, so map from A1 to here will extend to 0 too. And we would know that all elements away from 0 will go to n. And this means that 0 also shouldn't go to n. And this is how we find a translation here. And this is the topological argument. So let's realize this. But we start with the technical tool, technical lemma, which I called lemma 2. Let A, maybe I wouldn't prove it in fully, but I will discuss it. These are integers, integral domains. Also I have n positive integer. Then I can claim the following. Then we can characterize automorphism over A using automorphism over B in the following sense. out A of AM is endomorphisms. Okay, endomorphisms is just the same thing, but you don't require the inverse. Such that two things satisfied. F is invertible over B over B, and also Jacobian of F belongs to inverse element of A. We have such a lemma. So again, if we take some endomorphism which is invertible over B, but its Jacobian is invertible element of A, then actually this was an automorphism. Actually, it would be an automorphism. So yeah, here is the clear part, the obvious part is this inclusion here. If you have an automorphism, all these things are satisfied. This is obvious. And the other part is less obvious, but let me comment on it. If we have an endomorphism of AN and F invertible over B and Jacobian lies in invertible elements of A, I want to prove that actually this is an automorphism. This means that I want to prove that inverse also lie in this ring here. Okay, so
Excuse me.
yeah.
What does it mean F invertible over B?
I mean this F, as soon as it is an element of here, yeah. But also I have an embedding of integral domains. So this is an element here when I replace A by B. And invertible over B, I mean that actually it got to the automorphism over B.
That's it's not very clear because when you write down out A, AN, is it mean that A is invariance? So you do not use automorphism of A, but you just, each element of A is just fixed.
Yeah.
Am I right?
Yeah.
But why is each element of B is fixed? You say that you can replace A by B.
But we consider
Elements of B are not fixed.
we consider our F and
But
K over.
if I take this presentation over this string, I mean,
Here,
okay,
Inversible.
I can consider this element as an element of over the bigger ring, yeah?
Not because B is
Why?
not.
Just by writing the same coefficients.
This is a tuple of polynomials in coefficients
Yeah.
in A.
here,
Okay, just the same.
Just consider the same formula.
we
And
go.
require that there is a formula for inverse, but maybe with the coefficients from B.
Okay.
Okay, so let me show two quick reductions. First, we can assume that F preserves 0. Yeah. If not, then just shift, then multiply by translation. And if a new element will live here, then F will live here. This is the first thing, and the second thing we can assume that linear part of F is trivial. That F trivial, yeah.
Identity.
Identity is trivial. I mean, it looks like this. F1 it is x1 plus something, x2 plus something, xn plus something, and here, not here, but here, here, and here, all elements has degree at least 2.
You just multiply by an element of.
Yeah. We just multiply by the inverse element to the linear part. There is a question why linear part is invertible, but this is also needed, yeah? Jacobian of linear part will be the same. and it will live here, then this matrix has an inverse, and we can multiply by this. Here. Okay. So after this two reduction, this lemma is proven by induction. Okay.
Induction of n.
Induction on
On D.
On the degree.
wait a second. I will say a precise statement in a moment. I will present an index which will be an induction. So, yeah, we have after this reduction we have f, and we have its inverse in a bigger ring. Yeah, have f in inverse, which is equal to g, which we can write like this, and again gi we can decompose in homogeneous parts. I1 plus gi2 plus da plus gi sum d capital, which is the biggest of all degrees. Okay, this again, let me not write that this is a homogeneous part. Okay, clearly there are no part of degree 0 because g also preserves 0 and so on. So let me show by induction on J that Gij belongs actually to A of xi's. Okay. So actually base is here because the inverse linear part for G will be this inverse. I mean, linear part of G is the inverse of linear part of F, but linear part of F is trivial, so base looks like this. Gi1 are just x's. Okay. And formally I need to proceed here full induction, but let me just take a step from 1 to 2. And it will be clear, everything else will be clear. So step 1 to 2, we just need to write down the composition, G compose F. Since it is inverse, then its composition equals to this, which implies that Gi of F1 tata Fn equals to xi. Okay? But let me extend this formula. Extension will be like in the following way: xi is equal to from j equal to 1 to say d capital gij of x1 plus fi2 plus tata. Here will be x2 plus f22 plus tata. Xn plus fn2 plus tata. Okay. So formally, this base could be obtained from this formula by considering linear parts. Another possible way to prove this, but let us consider quadratic part. Quadratic part. It will be 0 equal to what? Equal to ji1 of f12. I mean f12, f22, tata fn2 plus gi2. Sorry. No, that's it. x1, xn. Okay. But by the base of induction, this lie in A, in a polynomial ring over A, yeah? And this is actually what I need to prove that lies over A. And so on, so on, so on. Clear? If something is not clear, you can ask questions. This is a very elementary, maybe a better explanation, but okay. this lemma is just our tool to determine that some inverse element also doesn't depend on there are no t's in denominator. We will apply this for the case. Here we have embedding of integral domains. We will apply this for embedding k of t lies in k of t and 1 over t. Okay. This is the case where it will be. Okay. So now I'm ready to go to a technical proof of theorem B, and I will be in time. So I'm erasing my sketch, and here it will be the full proof. Sorry for erasing this lemma, but this is, I will remind if someone forgets. Okay, so the main proposition for proof of theorem B is the following. And actually, Jeremy doesn't explain this sketch of proof, but of course he means it. And in his paper, you can find really this proposition. And if you look at this the first time, it could be unclear what's happening. But I wish, after all preliminaries, we will find that there are no strange things here. Let K be an infinite field. And again, a positive integer. G, some automorphism over polynomial ring, again of T, over AN, such that G of 0 doesn't, this is not an identity automorphism, but this is. Okay? So suppose we're given such G. Then, I didn't forget anything, okay. Then, and here are some technical things. There exists the pair of k-prime integers a and b, okay, k-prime integers, such that first thing which satisfied is the following. For any vector, epsilon 1, epsilon m, from your dimensional vector space, if we put the following element, we define by rho epsilon the following shift minus b, epsilon 1, x2 plus t in power minus b epsilon 2, xn plus t in power minus b epsilon n. Again, initially it lies here, k of t and t inverse. Yeah, it's an automorphism of a Laurent polynomial. Then if we conjugate and write this element, h epsilon, which is rho epsilon in power minus 1, g, but substituted t power a, and rho epsilon, actually lies in automorphisms k of t, of a n, and h epsilon of 0 is non-trivial, just a translation. this clearly lie in automorphism over the base field, is a translation. Okay, this is the formal statement which I was trying to sketch. I mean, if so far we have no such an element in our normal subgroup, such G, with this property. But if we find this, then we can, for any vector, consider such a shift, and by conjugation of G of t in power A, we will get family over all affine line. Not function, but all. And at 0, it will be a translation. Okay? And the second thing, it would be boring if each translation will be trivial. Then we will get nothing. But the second thing guarantees that there will be some non-trivial translations. I mean, for some epsilon. As set epsilon at IAN, such that H epsilon doesn't equal to trivial translation, trivial automorphism, open, yeah, clear, exactly, open and non-empty, or equivalent dense, yeah. Open dense. So, in particular, there is epsilon such that, yeah, this is a non-empty condition. So I claim that this is almost everything, almost all complexity of theorem B, and I wish I will prove it here.
Probably this is a point where we use the field to the infinite.
Exactly. Exactly. So it could happen that it will be always open. Yeah, but even if it's over finite field, say, it would be open, but it could be there are no rational points in this open set. But open and non-triviality of this set over infinite field guarantees that there are some rational points. By rational, I mean point defined over base field. So let us prove this. This is, I think that the last part you need to keep attention on all indices. So again, our favorite thing,
So you prove this proposition, right?
yeah, this is the proof of this proposition, and it's almost proof of TMB. I'll say some words after. Okay, so I have this description again. GIs are elements, but now they also depend on T, yeah? Because I have an automorphism from over polynomials here. So each GI is a polynomial in this number of variables. So, okay, what do we know? Also, we know that GI, if we substitute T equal to 0, it is equal to xi. This is this condition. Yeah? If we put 0 to T, then everything dies except this term. Okay, then this means that GI is equal to xi plus, and here will be 3 indexes, but I wish everything will be clear. I want to decompose it in powers of t, first of all, and in some powers also, but let me write it. G M Q I J M of x I x n times t in power j. where index m is about this. M is polynomial xi, xn, mth homogeneous part. Okay, we have this decomposition. Yeah. What I want to say about it, I want to put A over B be a maximum of the following thing: M over J for all Q, I, J, M, which are not equal to 0. So my theorem says that there are some coprime integers which are satisfying the following properties. Yeah, but this gives me that there will be coprime. This is just a formal thing. But why does it make sense? It doesn't make sense if all polynomials are 0. Yeah, all q's are 0. But this is not the case because we have this inequality. Yeah, my g is not identity. So there are some polynomials, and this is a nice defined thing. Okay, and then consider the following. Consider h epsilon, this h epsilon, h epsilon. I just want to make attention on it. Okay. Again, this clearly lives in automorphism over Laurent polynomials. But we are asked it to be from here. This is what we need to prove over polynomials. Okay? And how we will prove it? We just, again, need to expand this this thing. Okay, let me again write h epsilon like this: h epsilon 1 data h epsilon n, where each h epsilon is clear thing. Let me write down the formula and then comment it. It starts with xi, and then it, again, I want to decompose h epsilon I in powers of t. There will be linear term, term which doesn't depend on t will be the same xi, and then will be some formula. 0 q I j m of x1 plus t in power minus b epsilon 1, x2 plus t in power minus b epsilon 2, data xn plus t in power minus b epsilon n times t power a times j. So this is the last formula we need to concentrate on. First of all, let me comment on this. Why do we have linear part like this? Part which doesn't depend on t like this. What do? We first of all apply rho epsilon, which is of this form, yeah? And then apply g. We substitute it to g, which depends on t, like on t in power a. Yeah, and then we apply this inverse. If you think a bit, you will see that all thing which happens in linear term will cancel. Why? Because we have linear part, part which doesn't depend on t. I shift it by this vector, and then something strange happens in higher powers, but when I shift it back, a linear part becomes equal to this thing again. Okay? So, my claim is the following. This is a polynomial in T. Claim that this is actually a polynomial in T. But this is true in just by definition. You see, these m's are homogeneous of degree m, yeah, and it multiplies by t in power aj. So which power of t is in the denominator? It's m times b, yeah, and in numerator, its power is a times g. Yeah? So I need to understand, is it true that a times g greater or equal to than m times b? But this is true from the definition of a times a over b. Yeah? At this point, if you think, we can we can take a just large enough. It is not important to take a and b like this, but a large enough and b is something. Yeah? Just to kill all denominators. But it will be important in the second part. So, this is polynomials. Okay, so far I can say the following. Okay, let me write this. H epsilon lie in out k of t of an. Yeah? But again, this implication is not obvious because I should check that the inverse also doesn't depend on t. And here it is not that obvious because our conjugation not just by homotety but some strange thing. But this is this implication where we use this technical lemma. We just need to check that Jacobian is lying k of t and so on and so on. Okay, I just have no time, but this is there are no lie here. Okay, so this part. Let me state that this part is proved. Okay. Also, let us check what happens in zero. But okay, my space is out. I'm sorry for this, but I will write here. So h epsilon of 0. What is this? First of all, of course, it's okay, ice complement. I mean, it's a tuple ice complement. It's xi plus what? So I need to control where here I get degree 0 over of t. Yeah? Let me write like this. Plus sum where a times b equals m times j, q, which indices do I have? I, j, m of what? No, actually of epsilons. Epsilon 1, epsilon n. So let me denote these things by ci's. Some constants. Clear? So is it clear that h counted as 0 is a translation? At 0, its parts are xi's plus ci's. It's a translation. So, and here it is important why we ask a over b like this, not just large a, but like this, because we have, if we take this, we have some opportunity to have here non-zero elements. Because if a would be big enough, everything here will be divided by t and it becomes 0. But I want, in the second part, I want some non-trivial translation. And it is possible because of choice of a over b. So second thing which I will draw here because I don't want to erase the formulation. So what I want to say? Yeah, I want to say the following. what does it mean that h epsilon of 0 is a trivial automorphism? This is the same as to say that C1 tata Cn equals to 0, just by the form of h epsilon. Yeah? So then this is the same as to say that all this sum, which are these Ci's, let me just expand it, Qij m of epsilon equal to 0 for each I. Yes? And this is the closed condition in my affine space on epsilon. Yeah? So I need to avoid at least one of this condition, and this is the open set on epsilon. True? I need to check only one thing, that this is not the whole affine space. And this check is just about, I need to check that here there is at least one non-zero sum. This condition will give you a whole affine space if
non-constant sum.
I mean, if it's constant but not equal to 0, then it doesn't impose no condition. But I want to go to point which is not from this condition. I mean, this is h epsilon from 0 equal to ID, but I want to take a complement. So it's bad when all they are 0 because they all if they all are 0, then satisfying this condition give you a whole affine space, and there is no in the complement. So I need to check that these things, at least for one I, this is not a 0 polynomial. But if you think this follows again from the definition, you need to take such an index I where this equality satisfies, and then you will see that in this index I, here is summation on polynomials on different degree, homogeneous degree, because M determines G, and I mean, if you fix I, where there is at least one non-zero polynomial, then this summand contains different degree polynomials. Again, this is a quick check. I'm sorry because I have no time. But after this, after you show that here there is some, at least one non-zero polynomial, then this is not a trivial set. I mean, this is not a whole set. And there are points in the complement. And we proved two. Yes? We almost win. So let me finish theorem B and stop my talk. So I wouldn't erase the computation, but you see this formal proof is kind of, it's hard to follow this. You just write some polynomials, some indices, and so on, but the idea is clear. You need to just to formalize it, and it is tough. So proof of theorem B using this. Okay, let me remind what was happening. There was some non-trivial closed normal subgroup in SAut. K of AM. Okay, so the first step we already did. We take some element F, which is not identity, and live in normal subgroup. And again, I said if F is a translation, then we are done. So we can assume that F is not a translation. what are we doing there? So I need the following fact, or some complicated maybe exercise. This is the following. Since I have in the statement of theorem we have an infinite field. Since we have an infinite field, I claim that there is a translation x1 plus v1 xn plus vn, which doesn't commute with f. F tau prime doesn't equal to tau prime f. So this is because my field is infinite. So this is some complicated exercise, but I have no time to prove it. So
Complicated.
yeah, no, not trivial, not trivial. But okay, maybe someone know simple proof, but Jeremy have some two lemmas for it. Two like 1.5 of a paper. Not paper, but
So at least we don't see why we should use the condition that the field is infinite.
I mean, if field is finite, then you have finitely many translations here,
Yeah.
and it's not wondering that you can commute with all. No. I don't know. I'm not proving it, so it's just an intuition. So put a family of translation by tau, which is exactly this translation parameterized by t, plus t v1 xn plus t vn. What do I claim now? Okay, first of all, this lives in SAut over polynomials of an. This is true. Then consider the commutator. Consider the commutator G, which is not a coincidence that this is G and there was G. Tau inverse, F inverse, tau F. Clearly this lives in, again, automorphism over polynomials. Okay, consider this. Let me note some facts about it. Note that G is not an identity automorphism. Why is this? To check this, you should check these values at point 1. Yeah, since G of 1 is not identity. Yeah. No, exactly of 1. If you
Yes.
put it here 1, it becomes this, and this is there, don't compute, and this is not an identity. This is good. And also note that G of 0 is identity. Clearly, yeah? Because all elements, first of all, this doesn't depend on T indeterminate, so everything is clear. And if you put 0 here and 0 here, this is just conjugation by the trivial automorphism. So G of 0 is identity. But then, also let me note, also for any T0 which is not 0, G of T0 is in my normal subgroup. Yeah, because what is happening with G, it conjugate at any point, it conjugate of F inverse by some translation, which maps you to the group for any particular value, and then multiply by F. So this is true, yeah. But the punchline is the following. This G exactly satisfies this property. This is not an identity, but at 0 it is. Yeah. Then, by proposition, here we use proposition, there exists epsilon in my n-dimensional vector space such that H epsilon belongs to SAut over polynomials of an and h epsilon of 0 is non-trivial translation. Translation. Yeah? Just apply this. Moreover, this h epsilon is obtained from G by this formula. Yeah. And the final thing I want to say is the following. For any t which is not equal to 0, t0, h epsilon of t0 belongs to n. Indeed. This happens because for any non-zero t, if I put it here, yeah, it will be some element from n, yeah, because I said that for any t which is t0 which is not equal to 0, g of t is 0 in n, and then I conjugate by something which I can conjugate. Yeah. So I obtained such an h epsilon such that everywhere from 0 it belongs to n, and at 0 it's a non-trivial translation. So again, write our favorite picture. H epsilon give you a map to SAut over k of an, such that everywhere from 0 we get to our subgroup n, and away from 0 we are a non-trivial translation. But by continuity of this map, 0 also should map to n, because n is closed. So actually we have this picture, and 0 maps to some sigma here, which is non-trivial translation. And we found our non-trivial translation in n. And then we produce other things. Since we have one non-trivial translation by conjugation by SLN, we have all translations, and then we use theorem C, which I have no time to comment on, and get that all tame automorphisms lives in them. So this is one maybe unfair thing. I didn't mention the topology here and why this map is continuous, but actually there are a lot of topologies here. Okay, not a lot, but at least two natural topologies here. Also, if you work over complex numbers, there is induced topology by complex numbers topology, yeah? And in all of this topology, this map is continuous because it's polynomial map. So it's not strange, but formally you need to understand how topology looks like here, but I don't have time. And it's actually this is a complicated thing. All this is tricky, but not complicated. The topology of the structure of ind-group here is you need to be very careful. So that's it. I wish it was clear.
Thank you very much for such an interesting talk. And are there any questions? I have a question about TNC. You have not discussed it, but it seems that it's rather simple. Should be you just conjugate translations by something and obtain something which you build tame automorphism. It seems that when you conjugate translation by triangular, you obtain a triangle.
Yeah, well, there were two steps here from translations to Salem and from SAut.
Okay,
Yeah.
maybe two steps, but this is just direct.
Yeah, this is direct. It doesn't require any topology, and this is just writing some commutators.
My question is that if we think that this n should be a proper group, then there is some not tame automorphism which is not in this n.
Yeah.
And the only non-tame automorphism which we know is Nagata automorphism
Yeah, actually
in
it lies there.
three-dimensional. Yes?
If I'm not mistaken, Jeremy also said that Nagata automorphism lies there.
Yes, well, that was my question.
Yeah.
We can obtain the Nagata automorphism.
Yeah, if I'm not mistaken. I should check
It's,
it.
I believe.
It was checked by him. Yeah.
Okay.
And it's possible. Also, this is not the whole paper. Yeah, there are some notices about finite fields, and there is also a result about other normal closed subgroups in whole automorphism group. Okay, of course you have your SAut as a normal closed, yeah. But what do we have in intermediate? And there is a result that if you take your normal subgroup in the whole group and it maps surjectively to K star by Jacobian from this subgroup, then it should be the whole group. Also interesting result, and it uses this trick by conjugations by homothesis, which I present before proving this.
Okay, thank you.
So
And is it your field of research
No,
or
it's-
just for?
I'm doing some rational geometry, and Jeremy also doing some rational geometry, but also he's doing this stuff. And Kostya asks me to get into it,